the coordinate systems, various coordinate systems in your high school itself, but nevertheless, because as we saw last time, yesterday, we dealt with forces or understood what forces are, what the various kinds of forces are, and so on. And forces effectively are vectors, as are most physical quantities that we'll discuss in this course. So in general, by talking of fundamental kind of entities, what are the fundamental units that you know, or fundamental kind of physical parameters that you know?
Mass, time, length.
Exactly. Length, mass, and time. Right? So length, mass, and time would be the basics. Length, mass, and time. Why are they fundamental or elementary? Because every other physical quantity that you know of could be derived from these things. Velocity, acceleration, force, torque, momentum, whatnot. Every other physical quantity could be written in terms of length, mass, and time. Well, there is temperature as well, but that's a separate thing. Temperature in itself is fundamental, but that's a separate thing. You have units like degree Celsius or degree Fahrenheit for that. Current, yes. For current, true, it cannot be written in terms of length and mass. Current also involves another elementary kind of a unit, which is charge. Yeah. So that would be, starting from unit 2 onwards. But in general, whenever you talk of fundamental kind of units, length, mass, and time. And every other physical quantity in nature could be thought of either as scalars or vectors. What are scalars? Scalars are just quantities, physical quantities, which just have a magnitude. And vectors have both
Magnitude and direction.
Very good. So it would be, broadly speaking, scalars and vectors. What would be examples of scalars? Physical quantities. Current, I would kind of be skeptical of current because current does have a direction, not in the direction of in the sense of a loop. But we'll see in module 3 that I actually has a directional sense. But let's not discuss current. Yeah. Speed, very good. Even before speed, distance, exactly. Distance, speed. Okay, what else? Temperature maybe? Temperature? Okay.
Mass,
Mass, very
Time.
true. Mass.
time.
Okay. Time, yes, time. And you could come up with some more quantities, but roughly or kind of basically these are kind of the scalars that are kind of relevant to us. Okay. And vectors?
Displacement.
Exactly. So corresponding to distance, there would be displacement, velocity, good, velocity, acceleration, force, momentum, torque, and so on. Just to understand that you understand the difference between distance and displacement. Distance is what? How do you distinguish this distance with displacement or from displacement? Right. So if you take 2 points A and B in a two-dimensional space, like on the board itself, then the shortest distance between them is always a straight line. That's only if you have a 2D surface. But now, there might be multiple ways of reaching from A to B. They would constitute the corresponding distance. So you would reach from A to B this fashion, whatever. This one. Those would be distances. But the shortest one would be the displacement. And if you come back to point A, again, then the net distance, although is non-zero, the displacement is zero. So it's very crucial that you understand this difference between distance and displacement. Likewise between speed and velocity. Okay. So just the magnitude of the velocity is the speed. Attached to the vector, I mean whenever you talk of vectors, you also do have a directional sense that makes it a velocity. So there are instances when the average speed is zero, but the velocity is not. So we'll take up those problems later. But yeah, so fundamental units, scalars, vectors, all of this is again in the spirit of recapping things for you. And now we will see as to what the fundamentals of vectors are and basically the mathematics of vectors. So as you kind of know that vectors have properties of their own because they have this directional sense. So you just cannot add up two vectors as like two numbers. 3 plus 5 adds up to 8. That doesn't work for vectors. Why doesn't it work for vectors? Because they do have a directional sense to it. So we need to understand how to add up two vectors, how to subtract two vectors. Well, subtraction is again a process of addition because when you subtract, it's basically the minus of the vector that you are taking and adding it to the first vector. And there are these special operations which are called dot and vector products or cross products, which are absent in the case of scalars. But these are, this is the basis of the mathematics of vectors relevant to this course. We need to be clear on that. So, the remaining of this class will be talking of how to understand vectors, how to understand addition of vectors by taking up examples, and how to understand the basic two operations of vectors, the dot product and the vector. Okay. So, typically as you already know, that a vector, let's say A, it's a vectorial quantity, you write down the vector with an arrowhead on top of it, just to signify that you're talking of a vector quantity. And the way to graphically do it is you draw a straight line signifying the vector along with the direction. And typically the length of this arrow, let's say this is PQ, this is the vector A. The length of this arrow is typically the magnitude of the vector. So this is kind of basic, but obviously when you do it on paper or on the board, it's not to scale. You do not actually draw the actual length of the vector. If you say you're talking displacement of 1 meter, you do not actually draw 1 meter on paper, right? So if you are to compare vectors or draw vectors accordingly, you show a magnitude or a displacement of 1 meter with a longer arrow and maybe a displacement of 5 centimeters with a shorter arrow. That's how we do it. Okay. So basically, my point was the length of the vector or the size of this line is basically proportional to the magnitude of the vector. Now suppose you have two vectors, A, let's say this one is A, and you have another vector, let's say this one is B, and you have another vector, A. Okay. Now, how do you add up two vectors and what's the resultant? Right. So if you see that the resultant vectors, this is addition of vectors now. You have two vectors A and B. Let C be the resultant vector. Then the way to obtain C, graphically at least, is you start from the tail of A, the first vector, and join it to the head of B. So that would be your resultant vector C. This is all graphical. And at least in a two-dimensional sense, in a two-dimensional context, each of the vectors, or not only in a two-dimensional context, in a 3D space as well, vectors typically have components. Components along the x-axis and the y-axis. So, in order to understand that, or kind of get a feel for that as to why we need the coordinate system at all, is very crucial. So why do you think we need a coordinate system at all to kind of, what does the coordinate system do? Locate a point, right? Locate a point. Suppose you have a point here on the board, and without knowing a coordinate system, I ask you to locate this, irrespective of you and me, that is for the entire class. How is it that you can objectively define the location of this point? For that, you obviously need a reference axis. So that's exactly what the coordinate system does. Be it a 2D Cartesian coordinate system or the 3D, the purpose is to locate the point exactly. So in order to locate the point on the board, what I would typically do is choose maybe here, this point here, to be the origin, and say that the horizontal axis here is the x-axis and the vertical one is the y-axis. So typically what I do is I drop a perpendicular from this point onto the x-axis. That would give my x coordinate. I drop a perpendicular from this point onto the y-axis. That would give me the y coordinate. I would say that x and y, these two are my coordinate points. Right? Likewise, I mean this was perfect for a 2D case because the point is actually on a 2D surface like the board. Now if I ask you to pinpoint a location in this room, let's say the position of this marker pen, you'll see that it's no longer possible just with two numbers. X and Y are what? Just numbers. Two numbers with reference to some point which you have specified, that's the origin, popularly called the origin. Two numbers which exactly give you the location of the point. Suppose here lies the marker. You'll see that even if you choose, let's say the corner of this room, be this one or this one, is your origin now. Okay? So with respect to that, even if you say that the floor is like your xy plane, you will see that the position here is ambiguous. So you need a third direction to exactly specify the location of the marker or any point in space, in 3D space. That's why in general we have the x, y and the z system. This is all in Cartesian coordinates. X, y and z, what does it do? Again, basically three numbers which exactly give you the location. Okay, so for vectors, coming back to vectors again, vectors likewise is always usually specified with respect to some coordinate system. As such, they would have corresponding x and y components. So if you say that here is your x-axis and that's your y-axis, with this being the origin, 0, 0. And if you typically have a vector like this, let's say it's the point P, having coordinates x and y, and this is the vector A. Okay. And let's say it makes an angle theta with respect to the x-axis. Then the projection that this vector A makes on the y-axis or on the x-axis is something called the x component of it. Likewise, the projection. What is the projection? Projection is just like a very naive term. It's just like a shadow. Shadow of the vector onto the x-axis and the y-axis. So if you drop a perpendicular from the point P onto the x-axis, that would be your AX. So this is 90 degrees. Likewise, if you drop a perpendicular from P onto the y-axis, that would be your y. That is the y. So every vector in general could be written as Ax I cap. What is this I cap? I cap is a unit vector pointing along the x-axis. Let me just write it down. So any vector in general, we are talking of is a vector in general, can be written as Ax I cap plus Ay j cap. Ax is nothing but this length and Ay is this length. I cap is a unit vector. Unit vector means a vector of magnitude 1 pointing along the x-axis. So that's your Ax I cap and Ay j. Suppose it had been a 3D vector or a vector in 3D, then you additionally would have had a z component, then you would have Az k. So I, j and k, these things will keep on coming during this module as well as the rest of the course. So it's better to, that's why I kept this as the first kind of a lecture, just to make sure that we are on the same platform as to the understanding of vectors and scalars and so on. So typically this is how you will see vectors being written if at all in reference to the Cartesian system. Now the Cartesian system, the Cartesian coordinate system, is basically this x, y and z system, right? Now there are alternative systems of referring things. All these are what? All these are some reference systems. So you can alternatively come up with other reference systems which gives you the same information. So rather than specifying x, y, z, there is another alternative one called polar coordinate systems. So in polar, rather than having x, y, you have r, which is like the radius, theta, which is like the angle it makes with respect to the x-axis, and depending upon whether you are using a cylindrical coordinate system or a spherical one, I talk only of the cylindrical now, you have a z direction. So let's first of all not think about the z part. Let's say we are just in a 2D space. So it's only r and theta and x, y, and x and y. So from this diagram itself, we can find a connection between the two kinds of coordinate systems already. So x and y was pretty straightforward. Any questions till now regarding this? Yeah. So everything is in this diagram. You have x and y, you have theta, the angle it makes with respect to the positive x-axis, positive direction of the x-axis. So there are counts to how angles are counted or how angles are kind of referred to. There is a convention. If you take the angle from here to here, that's a positive sense. That's the counterclockwise sense. If you take the angle like this in a clockwise fashion, it usually comes with a minus sign. These are just conventions that's followed in mathematics or in physics in general. Okay, so now what we will do is we will connect the Cartesian system to the polar system, that is, we will relate x and y to r just from plain trigonometry. So this is Ax, and this being r is what? R is just the radius vector. starting from the origin, which is already here, to that particular point. So this is R. So now that you know this is R, and you know this is AX, AX is what I have been calling as X here. Okay, so if you want, I can just call it X. This is X here. This is Y. So what is R in terms of X and some trigonometric ratio?
Root of a sin theta.
Right. So X is, what should I write? Let me write it. So just from trigonometry, you can see that this being a right angle triangle here, this being the hypotenuse, the R, X being the base, X over R is base over hypotenuse, which is cosine theta. So X is just R cosine theta. Similarly, Y. Exactly. So Y is just R sine theta. What does that tell you? That tells you that if you know the polar coordinates already, R and theta, if I give you R and theta, you should be able to tell me what X and Y are. So you are transforming the coordinate system. Okay. What if I tell you X and Y and ask you what R and theta are? What do you do? From here? Yes.
Root of
Right. Very good. So basically, if you know R and theta and you want to find X and Y, the first thing to do is to find out the angle, which is very straightforward. You can divide this by this. So I'll call this equation 2, call this equation 1. So what I'm saying is you divide 2 by 1. What does that give you?
R is tan inverse x by y.
R's drop off. You just get tan theta equals y over x. That means theta tan inverse of
Y by x.
Likewise, if you square each of these equations and add them up,
X square plus square plus y square equals r square.
square and add. What do you get? You get R. I'll just write down the final result. X square plus y square. Sin square theta plus cosine square theta is 1. Okay. So knowing X and Y, you can get back the polar system. Okay. Okay. So let's see if I have any examples on this. So a quick short example of this on how. So we have already kind of gone through what addition of vectors are, and this Cartesian system and the polar system, and how vectors, at least in 2D, this is all 2D, just to keep things simple for the time being. Next we'll move on to higher dimensions. How to connect the Cartesian system and the polar system. So now we will take up an example where two vectors A and B are actually to be added and subtracted. Any questions at any stage, please feel free to ask. Okay? And questions are never stupid questions. I don't believe in them. Questions are always questions. There's nothing possible, no question possible, which is a stupid question. However silly, however basic, simple, naive it might seem, or sometimes, most of the times what happens is, what will others think if I ask a question? Get rid of all these are backdated kind of ideas. So nowadays we have all opened up a lot. So feel free to ask questions, however naive, however silly, however simple you might think it is. Okay, so an example. So you're given two vectors. So this is again the standard coordinate system, x and y axis. So one vector A, so these are displacement vectors. So this vector A has a magnitude of 3 centimeters. And it makes an angle of 60 degrees with respect to the x-axis. There is another vector B, again making an angle of 60 degrees, but now with respect to the negative x-axis. I shouldn't say the negative x-axis, but in the counterclockwise direction. Right? Makes an angle of 60 degrees, and the magnitude of this vector is 2 centimeters. So as you can see, these are displacement vectors because they are in centimeters. So you have to find out, number one, what is A plus B? Number two, what is A minus B?
A plus 2 is 1 by 2.
So what do we do? What should be the approach?
Components.
Any ideas?
Resolve into component.
Right, that's the easiest thing to do, as she suggests. That take the components of each of the vectors along the x and y components, along the x and y axis. Once you have the components of each of the vectors A and B, you can just add up each individual components to get the component of the resultant vector. Once you know the component of the resultant vector, the vector is known. Okay, so let's follow that. And first of all, what we'll do is find out the components of each of the vectors A and B. So A of Ax, which is the x component of A vector,
3 cos
is
60. 3 cos 60.
3 cosine 60. Right? So it's 3 cosine 60. Cosine 60 is half. Right? So it's just 3 over 2. Obviously, it picks up the centimeter here as well. It's a raw length. I'm just skipping right down to the centimeter. And Ay is
Sine
3
60.
sine 60, which is
3 root 3 by.
square root of 3 over 2. Good. Similarly, Bx,
2 cos minus 60.
2 cosine 60, and that is the projection here. So it's all positive, we are fine now. So it's 3 cosine 60, 2 cosine 60 now, which is 1. Cosine 60 being half. And what is By?
Minus 2 sine.
That's important. It's a minus. Why is it a minus? Because the projection here will be
Wow.
along the negative axis. So it picks up a minus sign. So it's 2 sine 60, which is minus
2 root 3 by 2.
2 square root. Good? All good, right?
By 2. Minus 2 square root of. Minus square root of 3.
Yeah, minus square root, sir. Yeah. I wanted to not write down this 2 actually because it cancels with this 2. But in fact, I did the opposite. So, yeah. So it's minus square root of 3. Okay. So now what would be the resultant then? That is A plus B. 1. So when you're adding up A plus B, all you're doing is individually adding up Ax plus Bx along the I component, along the x-axis, and Ay plus By along the y-axis. So basically, you have to just add up this,
5 by 2.
plus 1, y cap,
5
plus
3
square root of 3 over 2, minus square root of 3, whatever these numbers come out to be. So that would be simple as that. Now, if you have to not write it down in terms of I and j, and you have to actually graphically draw it in the diagram itself, if that's the question, and usually it's the question when they show a graphical representation of vectors. So the vector C, the resultant, vector A plus B, I haven't mentioned C here, so it's A plus B. will have a magnitude which is just the square of this added to the square of this taken the square root of. We are just following this. Right? So that will give you the magnitude of a plus b. I'll just write it down for completeness sake. So it's 3 over 2 plus 1.
Whole square.
You do the math. Try square root of 3 over 2 minus square root of 3 taking the square. But this is just the magnitude. Knowing the magnitude is half the job done for a vector. You need to find out the direction. How do you find out the direction? It's right here. In order to find out the direction, you basically have to find out the angle it makes with respect to the x-axis. That's all you do. So, the angle it makes is tan inverse of the y component divided by the x component. What is the y component? This entire thing. Try square root of 3 over 2 minus square root of 3 divided by 3 by 2 plus 1, which is this 2 by 2. So do the math, you get theta. So typically it would probably be lying somewhere here. I mean, this theta will actually tell you the angle that a plus b makes with respect to the x-axis. So, what about a minus b? Basically the same exercise repeated again. All you need to do now is revert the direction of b. Because a minus b is just a plus
B in opposite
of
direction.
minus. If you write it, it's like a plus of minus b. Good. So minus b is what? Minus b is just the vector b reversed. So vector like this. That's minus b. Preserving the same magnitude, but now the angle here is what? How much is this angle?
120.
120. That's it. It's 120. You can figure it out from simple geometry. So all you need to do now is take the corresponding components of the minus b vector. So the a vector we already know. It's done from the first part. So now we'll take the component of the minus b part. So this is part 2, a minus b. So bx, or better to call it minus bx, but I'll just stick to bx. So now the x component will actually pick up a minus sign, because the vector is like this, and its shadow or projection would lie on the minus x. So it's already a minus, and 2 cosine of 120. Okay. Or actually you do not have to do a minus here, because automatically the cosine 120 will pick up a minus. Why is that? Because it's lying in the second quadrant. You know this simple trigonometric thing, right? Every trigonometric ratio is positive in the first quadrant. So it's like all
Silver
sine,
T
tan, cos. Right? It's all sine, tan, cos. So cosine, because the vector b is now lying here, will pick up a minus sign. So you don't have to actually keep the minus sign. So by would just be 2 sine 120. And 2 sine 120 will be positive, because as you can see,
Sine is positive.
it will have a projection on the positive y-axis. Okay, so that being done, the rest of the exercise is just straightforward. You just have to repeat. Any questions? Yes? No. Okay, so that was a simple demonstration of how you add up vectors. Next we'll move on to actual operations on vectors, which are these: dot and cross product. Should I erase this?
Yes, sir.
vectors, because unlike scalars, they have a directional sense, as we know, do have other forms of operation that are associated with it. Scalars can only be added, subtracted, multiplied, divided, and so on. Vectors likewise, when they need to be kind of operated, we use this term operated, with another vector, we have to do something special to it, depending upon the context. So the first one is something called a dot product. If we have two vectors, A and B, the dot, or also called the scalar product of two vectors. So if you have two vectors A and B, and the angle between them, let's say again is theta. So A dot B is this operation A dot is this operation called the dot product, which is basically defined as
Magnitude of
the
A,
magnitude of A
magnitude
and the
of
magnitude of B
cosine of angle between
cosine
them.
of the angle
Between
between the two. And note that once you have taken the dot product, the resultant is just a scalar. That's why it's called a scalar product. If you have dotted two vectors, it's an operation which gives you the resultant parameter as a number, as a pure number, which is obviously a scalar. So that's where the term scalar comes from. Now, if you have to do it in terms of components, it's again straightforward to do. Suppose A has components like AXI plus AYJ in two dimensions. Again, you can include the K component as well. Let's forget about it for the time being. EXI plus BYJ, then A dot B would just be right. Just be this. Just have to multiply the corresponding X components and the Y components and add them together. That would be your A dot B. Now, what are the physical parameters that you can think of physical kind of quantities which usually show up as dot products? You all know this. What are the examples of dot products in physics? Work done, exactly. Work done is the first one. Work done is a dot product of what?
Force and displacement.
Force and displacement. Good. Work done. Any form of work done, be it mechanical or electrical, any form of work done could be written as the dot product of the force dotted with the displacement, which is typically given by S. Okay. Anything else that comes to your mind?
Torque.
Torque? No. Torque is the next one. Vector product. Anything else? Something from electromagnetic induction?
Lead.
Huh?
Magnetic.
It's the magnetic flux. Remember this quantity phi in Faraday's law? Right. So phi, what is phi? Phi is basically the magnetic flux, which is the dot product of the magnetic field and the area vector. B dot A. This is again going back to Faraday's law. B dot A is basically the magnetic flux. The flux itself is scalar. But you are getting it on the operation, the dot product operation of two vectors. These would be like examples that will become relevant when we actually discuss work energy principles or later in unit 3. Yeah, in unit 3 or unit 4 rather, okay, the magnetic flux. Okay. So that was pretty straightforward. Any questions? Let's move on to vector product. This, as you can see, is not an exhaustive exercise in vector mathematics. This is the bare minimum we would require in order to understand the remaining units, starting from unit 1. Because everything would be in vector notation, and in vector, we'll do these vector operations pretty often. So that's why this is the first kind of basic relation. Okay, and next is the cross or the vector product. So rather than A dot B, again the same situation, you have two vectors A and B, and the angle between them is theta. Basically, A cross B is the cross product, and it's given by the magnitude of A, the magnitude of B,
Sine of angle between them.
sine of the angle between the vectors, and something else.
K gap.
And when may or may not
Plane containing them.
some n cap, which is the normal unit vector or unit normal
Plane
vector.
containing them.
It's typically written as n cap. Now, what is the direction of n cap? How is it defined?
Perpendicular to the plane.
Right. Well, two directions are perpendicular to. If both these vectors are on the plane of the board as they are, two directions are there which are perpendicular to it. One is into the board and one is
Out
out
of
of the
the
plane of
board.
the board. How do you actually pinpoint the direction of
Right,
n?
fault is
What is the rule for that? Sorry? Some right input. That's right. So you rotate the vector A towards B. The direction in which your thumb points would be the direction of A. So in this case, A is like this, right? So rotate it towards B. You see that your thumb would tend to point into the plane of the board. So that's the direction of n cap. So I wouldn't say that's k cap because it may or may not be. When you say k cap, it's exactly along the z axis. So these vectors may not be exactly along the x and y. If they are, you're right. Then they are exactly along the z axis. Did you get that point? So if the two vectors are along x and y, then if you take the cross product, they would either be along the plus z or minus z. So then he is right that it would be k cap or minus k cap. But in general, n cap is what we use. Okay. And if you are given components, you can find out the cross product from the components as well. How is that? Exactly. That's through this determinant, where the determinant is basically specified like this. Okay. We all know what determinants are. Right? So if you are given the components of each of the vectors, you set up this determinant and find out the result and work out the determinant. That would give you, and the direction, as you can see, is inbuilt into the determinant. Once you take the determinant, I caps, j caps and k caps would be picked up. So the result would be including the vector. And as you can see, it's a vector product because the resultant is a vector. And what are again physical examples of this? Torque, right? Torque is given by R cross F. The radius vector crossed with the force vector. What else? Angular momentum. Right, angular momentum. L, which is R cross P, the linear momentum. What else? What else could be there? Torque, angular momentum. Yes. Anything else comes to mind? The magnetic force actually. If you have a point charge moving with a velocity v and it enters the magnetic field, then it's given by q v cross b. Remember? Q v cross b. So the force on a magnetic field for a point charge is given by q v cross b. So that's the cross product between the velocity and the magnetic. These are again examples we'll encounter later, but these would be physical examples of this. Okay. So let's end it up with a quick example of the vector product. So this is again an example. So whenever I write this EG, take it for, understand it henceforth that I am discussing a numerical example. Okay, so suppose you are given these three vectors. A, which is given by 3I minus 2j plus k cap. B, which is given by I cap minus 3j plus 5k. And C, which is given by 2I plus j minus 4k. You have to verify that these three sets of vectors actually make up a right angle. A right angle triangle.
Magnitude.
How do you do that?
Find magnitude.
So I'll just write down the question or kind of the problem in one line. Verify that the vectors form a right angle triangle. So what's the first thing you need to do?
Find magnitude. Not seriously.
Magnitude is 1, good. If you find out the magnitude of each of the vectors and add them, just use the Pythagoras theorem, then you can verify that actually, but even if two numbers they square are and you add them and it matches with the third number, doesn't really confirm that they are actually sides of the same triangle. You get my point? Suppose there is 3 and there is 4 and some other line is of unit 5. 3 square plus 4 square will give you 5 square.
A dot B equal.
Exactly. So somehow two of the vectors should be perpendicular. What does that mean? That means if you take a dot product of two vectors, they should be equal to 0. Does everyone get this?
Yes, sir.
So two things need to be verified. The dot product being 0, that would ensure that at least two sides are perpendicular to each other. Because the dot product, if theta is 90 degrees, then A dot B is 0. So you'll see that
Either or
it's A dot C. Verify that A dot C is actually 0. That means this vector A and the vector C are the two sides, not the hypotenuse.
Yes, sir.
The hypotenuse would be B. You can verify by doing this Pythagoras theorem kind of calculation. Find out the magnitude of each of these. Magnitude is again the square root of the components added up. The square of the components added up. Then, along with this argument that A dot C is 0, you can verify that these three are actually sides of a right angle. Okay, good. So we'll keep it here, and obviously I'll take your attendance.